Once we define a discrete random variable, the next natural question is how likely each possible value is. A probability distribution, also called a probability mass function, provides that information. It assigns a probability to every possible value the random variable can take. In notation, we write this as p of random variable x equal to lowercase x, meaning the probability that the random variable x equals a specific value lowercase x. A probability distribution allows us to describe the long-run behavior of a random process in a clear mathematical way. For a probability distribution to be valid, it must satisfy two essential conditions. First, probabilities must be non-negative and cannot exceed 1. In other words, every probability must lie between 0 and 1 inclusive. Second, the probabilities of all possible outcomes must sum to exactly 1. This reflects the fact that some outcome in the sample space must occur on every trial. These two rules are simple but fundamental and should always be checked before using a distribution in calculations. Why do probability distributions matter? A distribution summarizes how often each value of a random variable would appear if we repeated the experiment many times. Instead of listing every possible outcome of the experiment itself, we focus on the numerical values produced by the random variable and how likely each value is. This provides a compact and powerful description of randomness that forms the foundation for later ideas such as expected value, variance, and statistical modeling. Let's examine example 1 involving the number of mutated alleles carried by individual plants. The random variable x can take values 0, 1, 2, or 3, and each value has an associated probability listed in the table. This table is our probability distribution. Each entry tells us the likelihood of observing a particular number of allele copies in a plant from this genetic cross. Before using the distribution, we verify that it is valid. Every probability in the table lies between 0 and 1, satisfying the first condition. Next, we add them together. 0.5 plus 0.3 plus 0.15 plus 0.05 equals 1. Since both conditions are satisfied, this is a valid probability distribution. Performing this check should become a habit whenever you encounter a proposed distribution. Interpreting the distribution gives us insight into the underlying process. If we grew a large number of plants under the same conditions, we would expect about 50% to carry 0 copies of the allele, 30% to carry 1 copy, 15% to carry 2 copies, and 5% to carry 3 copies. The distribution describes these long-run proportions rather than predicting a single outcome for one plant. Probability distributions for discrete random variables are often displayed using bar charts. Each bar corresponds to one possible value of the random variable, and the height of the bar represents the probability of that value. This visual representation helps us quickly see which outcomes are most likely and how probability is distributed across possible values. When reading a probability bar chart, remember two key features. First, every possible value of the random variable must appear on the horizontal axis. Second, the heights of the bars represent probabilities, not counts. Together, these bars form a visual summary of the probability distribution, making patterns easier to interpret than from a table alone. Now let's look at example 2 involving medical testing. Here, the random variable y represents the number of infected animals in a sample of 5. The table lists probabilities for values from 0 through 5. This example shows a distribution with more possible outcomes than the previous one, but the same principles apply. Each outcome has a probability, and all probabilities together describe the behavior of the process. Interpreting this table, we see that the most likely result is 0 infected animals, reflecting that infections are relatively rare. As the number of infected animals increase, the probabilities decrease. This shape is common in situations where events are uncommon. Most observations cluster near 0, and large counts happen only occasionally. Again, we check validity. Every probability lies between 0 and 1, and the total probability sums to 1. Because these conditions hold, the table represents a valid probability distribution. Whether a distribution has 4 possible values or dozens, these two checks remain the same. Sometimes you will be given a proposed distribution and asked whether it is valid. The process is straightforward. First, verify that all probabilities are non-negative and at most 1. Second, add them together and confirm the total is 1, allowing for small rounding error. If either condition fails, the distribution cannot be used until corrected. These simple checks prevent many errors in probability analysis. If a distribution is not valid, it cannot represent real probabilities. In some cases, the issue may be a simple mistake, such as probabilities that do not sum exactly to 1 due to rounding. In other cases, the distribution must be rescaled or corrected entirely. Always confirm validity before computing expected values, variances, or any other properties. This step ensures your calculations are mathematically meaningful. The big picture is that probability distributions provide a complete summary of how a discrete random variable behaves over repeated trials. They assign probabilities to each possible value and allow us to move from raw randomness to structured analysis. These distributions form the basis for nearly everything that follows in probability and statistics, including measures of center and spread, model building, and prediction. Understanding them well is essential for future topics.